Welcome to TechnipFMC Tech Talk, where experts from around the company take you on a journey into various industry topics covering common trends that are coming next. My name's Andrew Manson, and I'm going to talk about the battery hybrid upgrade that we carried out on board the Deep Arctic. TechnipFMC are working to reduce the environmental impact of our operations, committing to reduce our Scope 1 and 2 greenhouse gas emissions by 50% by 2030, and that's versus our 2017 baseline year. In any given year, the offshore fleet of vessels can account for as much as 70% of our total group emissions, and therefore we need to have a strong focus on decarbonising our marine operations. And as part of our emission reduction roadmap for the fleet, we're going to focus on energy efficiency and reducing our fuel consumption. And in order to do that and to target where we can make those efficiency gains, we need good data analytics. So we've rolled out a digital platform throughout the fleet that's giving us access to good operational insight and energy consumption awareness that we need. So we've identified that battery hybrid upgrades can provide that step change in vessel efficiency. And so they'll play a major part in our emission reduction program. And today I'm going to explain on board the vessel how that works on the industry's first battery hybrid diving support vessel. So first, let me introduce the vessel, the Deep Arctic, a saturation diving support vessel, or DSV. And the vessel works on offshore construction, inspection, repair and maintenance, or IRM activities. Introduced in 2009 as one of the most modern dive vessels in the world, the vessel has a 24-person saturation dive system on board, where teams of divers live and can be deployed using dive bells down to water depths of up to 350 meters. And we can carry out those dive operations, launching and recovering and diving in quite severe weather, in sea states up to significant wave heights of HS6 or 6 meters. The vessel can do that quite often in close proximity to offshore installations or platforms, whilst divers are working on the seabed on sometimes critical subsea infrastructure. And it's not just diving operations that are happening. We can be deploying loads to the seabed using our subsea cranes. We can have work class and observation ROVs, or remotely operated vehicles, all working on simultaneous operations. And so you can see it's critical that the vessel holds station above that work site, above those divers, especially considering that the diver's life support is entirely dependent on their umbilical connection back to the vessel. So we need to ensure that we can hold station even in the event of equipment or system failure. And to do that, we require high levels of redundancy on board the vessel. And that's where we start to introduce inefficiencies. So let's talk about how the vessel holds station. The vessel has a dynamic positioning, or DP system. And that system is made up of dual redundant power generation, distribution and control systems. And those systems are designed to feel safe or be fault tolerant even in the event of a severe incident like a fire or flood on board. And we'll always have enough spare power and thrust so that we can hold station and safely abandon the operations. So first of all, we'll start with the power generation. We have 2 engine rooms on board, and each engine room has 3 engines, around about 3.3 megawatts each. And those engines, or generators, supply electrical power to switchboards within independent switchboard rooms. And from the switchboards, we supply power to independent groups of thrusters in the forward and aft end of the vessel. And all of these compartments, engine rooms, switchboard rooms, thruster rooms, they're all separated by fire-rated watertight bulkheads. And so in order to set the vessel up in the safest mode of operation possible, we would normally run 2 engines within each engine room. So 4 engines running all together. And in normal operable conditions offshore when we're diving, those engines would be running at quite low load, around 15 or 20%. So unfortunately, running engines like that at such low load is very inefficient in terms of fuel consumption. So whilst that's great in terms of operational redundancy, if we lose a single engine, the other engine in that engine room simply ramps up and takes the load. We never lose power to any systems or equipment, but it's very inefficient from fuel consumption point of view. What we really want to do, we want to run a single engine in each engine room and run those engines at a higher load, up to 30 to 40% load. And that's where we get the step change in efficiency. But what can happen then if you imagine we lose an engine? The other engine in the other engine room can simply ramp up, it'll supply power to the remaining thrusters and we'll hold station. But we can lose power to parts of mission critical equipment on board. We can lose power to parts of dive systems, cranes and ROVs. Now, whilst all of these systems are designed to handle that and to continue running at reduced load or to feel safe, we don't really want to be in a position where we're relying on those safety backup systems. So we don't tend to operate like that. And that's where batteries can come in, or energy storage can come in, providing that short-term power backup and giving us that operational spinning reserve. So Thomas, Chief Engineer on board, could you give us your perspective on operations with the batteries? It's very good. The batteries require very little maintenance, also as the associated auxiliary equipment, which is installed together with the hybrid system. What is important to remember that this upgrade got a big influence over the machinery and propulsion of the vessel. A power plant is driven by engines, and by reducing the number of engines running, we're reducing running hours of these engines. Maintenance of the engines is based on the running hours, and when we can do the maintenance less frequently, we save money on labor by third parties and also by buying less spare parts. Thank you. So let's talk about how batteries can bring efficiencies. We have a number of modes. First of all, we have that power backup function, where those batteries can replace spinning reserve from engines and give us that power backup function and that operational spinning reserve that we need. Then we have peak shaving and enhanced dynamic performance. Peak shaving, if you can imagine, where we have cyclic loading on the engines, the batteries can reduce that, allow the engines to run on a steady state load. That gives us some fuel saving and also reduces wear and tear on the engines. We also have a scenario whereby if we like to start large consumers like the main crane, we get peak loads. Again, the batteries can shave those peak loads, and that avoids us needing to start additional gensets. And then we have enhanced dynamic performance. That's where batteries work with the generators, providing instantaneous power on demand. So you can imagine we're offshore in DP, there's a large gust of wind or a squall, the thrusters demand load from the engines and we have a turbo lag normally. With batteries, we have no turbo lag, we have millisecond response, giving us a much safer and more dynamic vessel. Then, if we imagine we can combine all of those together to get potentially zero emission operations in port. For example, in port, we still have divers living in saturation. We still are carrying out critical crane loads over the back deck. And if we're reliant on a single source of power from the shore side, if we lose that, we can black out the vessel. So then again, we use the batteries for that power backup function and that peak shaving function, and that allows us to rely solely on shore power and to safely carry out operations in port. So within each of the battery rooms on board, we've got 2 cubicles of batteries, and in there we have around 420 kilowatt hours of energy storage in each battery array. Now, it's a lithium-based technology, and like a lot of other lithium-based applications, we can't use all of that energy storage. If we cycle the batteries full to empty too many times, we'll very quickly degrade them and shorten their life. So we protect them by having depth of discharge margins, max charging margins, and we also build in an aging allowance because we do expect wear and tear and degradation on the batteries through their life. Then we're left with that middle working capacity of the batteries. There we have the peak shaving allowance, and we have that power backup allowance, and that power backup allowance must always be available. So what does 420 kilowatt hours of energy storage actually mean? So let's put it into context, then we can compare it, for example, to an electric car or an electric road vehicle or an EV. The typical electric car has something like 70 or 80 kilowatt hours of energy storage. So then you can see we have the equivalent of around about 6 of those EVs within each battery array on board. But unlike an electric vehicle that can maybe have a range of something like 200 miles, we can't operate a ship like Deep Arctic on battery power for very long at all. The deep Arctic in a typical day would consume something like 60 or 70,000 kilowatt hours of energy. So you can see then we're talking about having 1,000 road cars equivalent on board to operate for just a single day, whereas we normally operate offshore for a number of weeks. So we rely on battery power simply for that short-term power backup. So it's important then to note that it's not just a simple plug and play of batteries on board. There's a lot of other hardware and interfacing that's required to make them work. So we have the batteries. The batteries operate on a DC power. We need to convert that to AC power and back, so then we have variable frequency drives. We need to then transform between various working voltages on board, so we have transformers. And then we have high voltage and low voltage distribution boards in order to get that power to the vessel switchboards and to all of the other auxiliary equipment that we need. Now it's important with lithium batteries to control the temperature, and we do that by pumping cooling water through the batteries themselves and also air conditioning the rooms that the batteries are in. So that requires us to have additional cooling systems. We have additional seawater, freshwater and chilled water cooling systems on board as well. Then we have the other ancillary systems that we need in the battery rooms. Of course, we need fire detection, firefighting, CCTV, alarms, and so on. And then on the control side, we have a number of things we need to do there with interfacing. We need to ensure that the battery management system is communicating with the vessel power management system to make sure that we have that power on demand when we need it. We need to make sure that the engineers can monitor the state of health with the batteries and all of the other systems that we mentioned, and they must do that from the engine control room. So we have to interface all of that with the integrated automation system, or IAS. And then finally we need to make sure that the DP operator, the dynamic positioning operator on the bridge, has information all the time on the state of health and state of charge of the batteries in case he needs to give the command to start standby engines. So Norbert, as vessel master on board the Deep Arctic, could you provide some of your operational experience from having the batteries on board?
Yeah, indeed. I cannot think about anything else but divers' safety, and this system has improved or increased this safety level, quite significantly. Actually, by adding those batteries into our system, we have changed our redundancy concept, which allow divers to evacuate, in the case of some emergency. This gives them a little bit more time to do so.
And in terms of vessel performance?
Well, we're receiving very good feedback from the clients. They are very happy, us using the hybrid system on board. This is causing quite a big fuel savings and big gas emission reduction.
Thank you. So now let's talk about the emission reduction benefits. So fundamentally, we want to run fewer engines at higher load where they run more efficiently. So let's look at each mode of operation. When the vessel's in port, we can reduce from 2 engines down to 1, or potentially to 0 engines where we have that shore power infrastructure available. When the vessel's in transit, we don't reduce the number of engines, but we benefit from that peak shaving we discussed. And finally, we have when the vessel's offshore working in DP, as we described, we reduce from 4 engines down to 2. So if we take those modes across an average year for Deep Arctic, we expect to see savings of anything up to 20% in fuel and emissions, as well as around 50% reduction in engine maintenance and running hours. And it's not just greenhouse gas emission reduction. We also reduce local air pollutants by running our engines more efficiently. We reduce the particulate matter or soot, and we also reduce the NOx and SOx. So we can conclude that the battery hybrid upgrade on board Deep Arctic has provided a step change in energy efficiency and emission reduction, and it's helping reduce the cost and the environmental impact of our operations at TechnipFMC. So that's it from the Deep Arctic. I hope you've enjoyed it, and please do subscribe to our Tech Talk communications to see future releases.